Okay, so we're gonna start by talking about acids and bases. We talked about it a long time ago, like back in October. So just a quick definition. Now there are multiple definitions of acids and bases, so we'll kind of go through them from general to a bit more specific. Okay, easiest way I think to identify most acids and bases is acids. They increase H plus concentration when you dissolve them in water, and a base is something that increases hydroxide concentration in water, so more of me. Okay, so if you guys notice, example of an arrhenius acid, so the type of acid we're talking about right now is HCl, because when it's in water, it breaks up into H plus and Cl minus, which will obviously increase the concentration of H plus. And same thing with NaOH, but with hydroxide. Okay. Easiest way to think about it. Okay. So this is how I personally still think about acids and bases. It's just the most general, easiest way to think about it. The thing that you do need to keep in mind is that there are limitations to this. So there are bases, it's usually with bases that don't produce OH minus, and they're still considered bases, but we'll talk about that in a second. Okay. All right. Any questions on that? I think that's the easiest definition. Acids increase H plus, bases increase OH minus. All right, the second definition of acids that we'll talk about are called Bronsted-Lowry. Okay, and this is where we get the definition based on the fact that in acid-base reactions, protons or H plus is transferred from one substance to another. Okay, so for example, when HCl breaks up into H plus and Cl minus, inside of water, basically what could happen is that this H plus can be used as an H plus donor. So it could, HCl donates H plus to water to make it into hydronium right here. Okay, so this is the instance how we can see HCl as an acid. Okay, because HCl donates a proton. Okay, so if we want to write that kind of simply, an acid in this definition is an H plus donor. Okay, and then a base is going to be an H plus acceptor. Okay, so compounds that give H plus to other compounds are acids in this definition. Compounds that receives H plus is going to be a base. Okay. Dude, we started like 4 minutes ago. Yeah. Robert's dad, if you're watching this, your son has not started his notes yet. Okay. Actually, I've watched the lesson in like 3 months. All right, I'm gonna send him a message then. Sure, Dolly, you have to watch this one. This is my best one yet. All right, so if we kind of look at this equation right here, this is just what we looked at. HCl is going to give H plus to water. So it's going to be the acid. Water is going to receive an H plus, and that's why it's a base. Okay, just basically what we talked about. Okay, it's that red one. The red one gets transferred from HCl to water. Okay, so that's one of the other definitions, and I have it written down what we just wrote. Okay, so let's go into 12.1. I want you guys to take a look at this reaction. There is an acid and there's a base. I just want you guys to identify which one's the acid and which one's the base. I'll give you like a minute to do it. Alrighty, any brave soul want to share which one they think the acid is? Yeah, Robbie.
I think the acid is NH3.
NH3. Why do you think NH3 is the acid?
Because it gains a hydrogen from the CLH.
It does gain a hydrogen, but let's look at the definition. An acid does what? It donates. Yeah, so you are correct.
Did I say base?
Yes, you said this is the acid.
Oh, I meant that's the base.
Yes, you are right. You are right. Yeah. No takebacks. Okay, yeah. So this is going to be the acid, and this is going to be the base. So because like Robbie enlightened us, NH 3 is going to accept an H from HCl, and that's why it becomes ammonium right here. Okay, so pretty easy. Now, if you guys notice, it's a little bit more specific than the definition we got last time because there's no hydroxide that's involved inside of this reaction, right? Yeah.
Base NH3.
Yeah, this is the base. No, that's going to be for later. Yeah, but yeah, this one is the acid and this one is the base. Okay.
When we like say whether it's an acid or a base, do we have to say whether like in the book there's like it's an Arrhenius.
Yeah, you won't have to know the specific type of acid for the AP test. Yeah. Yeah.
Oh yeah, talk about like between acid and acid.
I don't know. I'm making this up as I go. We'll figure it out. All right. Yep. You have been. All right. Let's do this one really quickly too. I'll give you guys like 30 seconds just so we get used to this. So 12.2. 30 seconds to figure out which one's the acid, which one's the base. All right, guys, let's go over it. Does any other brave soul want to share which one they think is the acid? Yeah, Josie.
But H2O is the acid.
Okay, yeah, so H2O is the acid because if you notice, it gives away a hydrogen to the NH3, and so this is going to be the base. Okay.
Oh, it's NH3O.
It's usually going to be the base, yeah. We'll talk about what determines it
Okay.
in a sec, but you guys are getting way ahead of me. Yeah.
I thought H2O was.
Yeah, so that's one thing, yeah, I wanted to point out because in the one of the previous reactions, we had HCl and H2O. And in that situation, HCl was an acid and water was the base, right? But so we're actually gonna talk about that right now. This right down here. So water is one of those examples of compounds that can act as an acid or base very readily, and we call that amphiprotic. Amphiprotic, which means that it can be either it can act as an acid or a base, depending on what compound it's reacting with. Yeah. We'll talk about that too. Yes.
Is there like a set amount of stuff that you can do that or just change?
So technically everything is amphiprotic. Some are just more inclined to be than others. We'll talk about that too in a bit. And I'm pushing this all later. It's because we're going to talk about it later and I don't want to repeat myself.
No,
I hate repeating myself.
you can overthink it.
Dude, I do. You're so right. All right. Anyway, one thing that I do want to point out is that an acid and a base, they must always work together to transfer a proton. Okay. Basically, that means that something can only be an acid if it is reacting with something that can act as a base. Okay, so if it's just sitting there by itself, it's technically not an acid or a base. It's only an acid or base when it reacts with something. Okay. Basically, acidity and basicity is relative. Okay. Okay, so let us take a look at 12.3, and that's going to actually help us with the next concept we're going to talk about. Okay, so if you guys take a look at this reaction right here, you guys don't need to write this down, but let's just take a look at it. Which one do you think is the acid? Which one gives a proton? Yeah, H2S. You notice H2S becomes HS, right? So it loses a proton. So it's going to be an acid, which means obviously this guy is going to be a base. Okay, now, if you take a look at this reaction, it is reversible, right? It goes both ways, which means on the other side, we can take a look at it from the other side as well. So if we take a look at the other side of the reaction, okay, and let's say we're going this way, we're going backwards. Okay, in this situation, which compound is giving the proton if we're going the other way? Yeah, this long one right here. This guy right here, when we go in reverse, this one is acting as the acid, and this guy is receiving the proton, right? Do you guys see that? And so if you guys notice, depending on which direction we are looking at, remember, this is basically the same thing as this. A compound can act as an acid or base depending on which way the reaction is going. Okay, and this guy is obviously the same thing as this guy. Do you guys see that? They're kind of like the same thing, but depending on which way you go, the only thing moving is that proton between the two. Yeah.
It's like every reaction.
Yeah, most acid-base reactions are reversible. There are some that are very strongly inclined to go one way, and those are the ones we'll memorize.
Are they usually like in the word reaction, the products are usually ions?
Yeah, usually. Yeah, because the proton is being transferred. Yeah. Okay, so that gets into what I was just what the next topic. The next topic is about conjugate acid-base pairs. Now, if you guys notice, again, this guy on the left side, H2S, is an acid, but on the right side of the equation, it's going to be a base. These two compounds are basically called conjugate pairs. Okay, conjugate pairs. Okay, and conjugate pairs are basically two compounds in a reaction, one on the left, one on the right, which is the same thing. The only difference is the proton is moving around. And so on one side of the reaction, it's going to be an acid. On the other side, it's going to be a base. Okay, so these two are conjugate pairs, and then obviously the other one is also conjugate pairs. Okay, so if we want to write the more technical term, on the right side of the arrow, HS minus is the conjugate base of this acid. And this compound right here is the conjugate acid of this compound right here. Okay, so conjugate just means basically the opposite of that. Okay, whether it's an acid or base. And that's what basically all this text is about. And again, the only difference between a conjugate acid and an acid and its conjugate is going to be the proton, the H plus. Yes.
So it's not like the two acids are together, it's the acid and the base. And the base.
Yeah. Yeah, opposite sides of the reaction. Yeah. Make sense? We're keeping it easy before it gets really hard.
Yeah, this will get just what's the
Conjugate, yeah, actually there are usually a good chance you'll see a conjugate question. Easy clap, right? Easy. Okay, so if it's so easy, let's try a problem. Okay, so I'm gonna give you guys about maybe about 2 minutes to try 12.4. If you want to try 12.5, I think you guys can do it, but we'll go over in a second. But take about 2 minutes, at least try to get 12.4 down. Basically, you're trying to find the acid and its conjugate base, and the base and the conjugate acid. Okay. Okay, so if we take a look at 12.4, who thinks this is an acid? Who thinks this is a base? Yes, this is the base. Great job, everybody. NH3 is the base because if you notice on this side, it gains a proton. So what term do we call NH4 plus then?
Acid.
Conjugate acid. Good. Conjugate acid. Okay, and again, these are related. They're like cousins. All right, let's go to this one. Obviously, that means that water is going to be your acid, and hydroxide is going to be the conjugate base. Good. All right, cool. Now, if you guys notice, if you guys want to jot this down, just so you kind of have another way to reinforce that knowledge. When the conjugate base is basically going to have, it's going to lose a proton. Okay, whereas the conjugate acid is going to gain a proton. Okay, so conjugate bases lose an H plus relative to the acid, and a conjugate acid gains H plus relative to the base. Okay.
It's always hydrogen.
Yes, it is always hydrogen. Okay. So that'll help us with this next question. What is the conjugate base of? So if we take a look at this term, conjugate base, it means that the compound is going to lose H plus. Okay, so that makes these problems pretty easy to solve, right? You just take away an H plus from this guy, it will be ClO4 minus. You take away H plus from this, it'll be HS minus. And again, it's because you're losing a positive charge. You take a look at this, what's it gonna be? Yes, just pH 3 because it was positive, so it goes down to neutral. And then last but not least, we got this one, and this is going to be CO3 2 minus. Okay. So that's going to be the conjugate base. And obviously, if I ask for the conjugate acid, you would just add an H plus to it. Okay. Any questions? Guys chilling? Cool. Okay, we're gonna jump down a little bit from here. We're gonna skip 12.6 because conjugate acid just put a H plus on it. Okay, we're gonna take a look at 12.7 now. And 12.7, we have this compound right here, this ion, okay, and it's amphiprotic. Okay, so it can act as an acid or base. So what I want you guys to do is I want you guys to write an equation for the reaction of this compound with water. But in the first one, part A, I want you to write an equation where hydrogen sulfide is an acid. And for B, I want you to write it where it's a base. Okay, so see if you can write an equation. Now, if you guys need a little bit of clarification, okay, the reactant side is going to be the same for both of them. You're going to start with HSO3 minus and water for both of them. Okay, but the products are going to be different. Okay, so on part A, I want you to do the equation where hydrogen sulfide is an acid. And here, I want you to write it for when it acts as a base. Okay, so it's a good way to see you guys really understand what the conjugates are, how the hydrogen should move when it's an acid or base. So give you guys about 2 minutes to do that, and then we'll go over it together. So I talking about, okay, so here in A, you want hydrogen sulfide to act as an acid. Now, for an acid, does an acid donate or receive an H plus? Yeah, this guy is going to donate, which means you got to take the H plus here and give it to water, which means on the right side of the arrow, we're going to have SO3 minus, and then you're going to have H3O plus. Thank you. 2 minus. Appreciate that. See, I'm losing my touch already. All right, SO3 2 minus. All right, so obviously, if we want to label it, this is the acid, this is the base, this is the conjugate base, and this is the conjugate acid. Okay. All right. That makes this next one really easy. The base is going to accept an H plus, which means that on the right side of the arrow, we'll have H2SO3 plus OH minus, where this is going to be the base. Water acts as your acid. You got your conjugate acid, and you got your conjugate base. Yes. No, because it was negative, and so if it gains an H plus, the negative one goes to 0. Yeah, so it's neutral. Yeah, good question. Yeah, always check with me on the charges because I get messed up too. A lot of things to keep track of. Okay, make sense? Easy peasy. Okay, let's move on. So we're going to talk about the relative strengths of acids and bases. So like I told you before, acidity and basicity is relative. Okay, some compounds are better at giving up their protons. They're weaker. And some of them are better at gaining protons. They're the bullies that steal the H plus from the acids. Okay, so some bullies are stronger. Some victims are weaker. Yeah. What's up? Yes, it does have to do with polarity. That's going to be a thing. Great point. But we'll get to that in a sec. Okay, now, there are types of acids. You guys don't need to... Actually, you guys do need to know this. Sorry. The first is a strong acid. And strong acids completely transfer their protons to water. Yeah, we've talked about this before. So let me do the strong acids in pink. So when we write an equation, let's say H, because obviously it's going to be giving up the H plus, and we'll do X as our, the other part of it. Strong acids, we use a arrow that just goes right because it completely dissociates when you put it inside of water. Okay. So this is going to be a strong acid. Okay, and it dissociates completely inside of water. Okay, that's why we just draw this arrow. We don't do the equilibrium arrow because it's not going to go backward. This is like Taylor Swift and Taylor Lautner. They break up, they done. They're never getting back together. Yeah.
So they're never reversible.
No, they're never reversible. Yeah. We are never, ever, ever getting back together. Like ever. Oh, she has. Anyway, yeah. Now, one thing we do need to know about this is that the conjugate base, so this is going to be your conjugate, right? This conjugate base is super weak. Okay, because obviously it makes sense. It's not reversible, so that means it's super weak. It's really hard to accept an H plus. Okay. So strong acids have really weak conjugate bases, okay? Because again, it doesn't want to turn back into the strong acid. Okay? It likes to break up and stay broken up. Make sense? Okay. We'll go to the next one. This one I'll do in blue. Weak acids, so HX. These are the ones that we're going to use the reversible reactions for. It's going to break up into H, same thing, H plus and X minus. Now, this is going to depend on some factors, so we can't say everything for sure, but weak acids, as you can see by the arrow, they can have reversible reactions. Okay, and the strength of the conjugate base is going to be relative to how strong this weak acid was, the strength of that weak acid. Okay, we'll talk about that in a sec, though. So far, so good? Yeah. Yeah. All right. Next one, number 3, compounds with negligible acidity. Basically, these are going to be your bases. Okay. So there are compounds that have hydrogen in them. So for example, NH3, it's a good example. There's 3 hydrogens, but they don't really like giving up their hydrogen, so they don't act as acids. Basically, they're bases. Okay, so those are the 3 types of acids. With the third one kind of not being an acid, but it is what it is. Okay, any questions on that? Make sense? Easy peasy? Okie dokie. Hi. Not that I know of. Let me see. No, it looks good. Yeah, I'm loading videos. All right, let's move on. Okay, so beneath here, I have a little handy dandy chart. Now, you guys have to memorize this. If you don't, I don't really care. You don't have to. No, you don't have to memorize it. I'm joking. I'm just joking. No, yeah, so you'll just have to know the strong ones, but we'll talk about that later. Now, I just want to show you guys how to use this chart. Super simple. So if you guys notice, if you got a compound that's a very strong acid, its conjugate is right here. Its conjugate is going to be a very weak base, almost it's not even a base. It's how weak it is. Okay, but if you have a very weak acid, that means the conjugate base is going to be very, very strong. Okay, so just keep that in mind. The strength is going to be relative to its conjugate. You got a strong acid, you got a weak conjugate base. Okay, you got a weak acid, you got a strong conjugate base. Okay, it's just basically opposite of one another. Okay, make sense? All right, so with that being said, I want you guys to just see if you can write this almost FRQ style. Very simple sentence, just one sentence, 1 or 2. Okay, so HClO4 is a strong acid. It's one of the ones you'll have to memorize. But HClO4 is a strong acid. What do you think the basicity of ClO4 minus is going to be? Okay, so just write that down on your paper. First, you want to answer the question very directly. You want to say it's a strong base or it's a weak base, and then give a short explanation why. Take about 2 minutes to do that. And let's go on to 12.8. Okay, 12.8. Okay, guys. So, how would you classify the basicity of ClO4 minus? Yeah, very negligible or very weak. You can just say, yeah, negligible, very weak, something like that. Yeah, so basically, very weak is negligible, 0, close to 0. Yeah. What was I saying? Yeah, because HClO4 is a strong acid, and the reaction is not reversible. Something like that. As long as you talk about how HClO4 is a strong acid, strong acids don't like coming back together. If you want to mention Taylor Swift, go ahead. We'll probably give the AP reader a chuckle. Yeah.
So then you have to memorize the strong ones, but that means you only have to memorize like 3 because they're just the.
There's more than 3.
Because you just have the conjugates of the strongs.
Yeah, those are all. There's always going to be weak, but there's strong. Yeah, you're going to need to memorize the strong acid, strong bases. You don't need to memorize weak or anything. Yeah. All right. Yeah, let's move on. Everyone cool with that? Yes.
So if it's like a conjugate, it's like is it better to say like it's negligible?
Either is fine. Negligible is probably the more correct answer, but if you write weak or very weak, that's fine as well. Yeah.
I thought that it's weak conjugate. Or
Yeah, you can
say
say this is the conjugate base of this compound, which makes it very weak. That works too. Yeah.
Oh, that's not helpful.
Okay, let's do 12.9. Okay, so 12.9, we got HCl, which is a strong acid, and it's represented in the reaction here below, reaction with water. Okay, let's take a look at the strength of the base and the conjugate base. Okay, so we said that HCl is a strong acid. Okay, which means the conjugate is gonna be what?
Oh no, I was saying.
Oh, okay. Yeah, what was the question?
Oh, it was because you said like the reaction power.
Yeah, so you're alluding to the reaction. Yeah, if you want to allude to it, that's fine. Strong acid, you're supposed to know that they're non-reversible. Yeah, good question though. Okay, so yeah, HCl is a strong acid, which means the conjugate is a what?
Weak base.
Yeah, weak base, very weak base. Okay, remember, they break up, can't get him back. Can't get Taylor back. Don't want Taylor back. All right, anyway. Okay, so let's talk about the relative strength then of the conjugate base. So this is the conjugate, right? Oh, sorry, I should have written weak conjugate base. Okay, and which compound here is the base?
H2O.
H2O. H2O is the base. Okay, so we got the base and we got Cl, which is a weak conjugate base. Let's talk about the relative strength. Which one do you think is a stronger base?
H2O.
Yeah, whoa, that was quick. Yes, you guys are so intelligent. Yeah.
Gold star stickers. Right there.
No, I'm kidding. I'd be only giving it to like myself. All right. No, not even Ian. Not 100%. No, don't deserve it.
100%.
Yeah, I gotta pull up the Asian education scale. All right. Anyway, so yeah, so H2O is a stronger base than Cl minus. Why? Why is H2O stronger base than Cl minus? Yes.
Because H2O on the scale isn't as strong.
Yeah, but let's assume we don't have the scale.
Oh.
Yeah. No, it's not because of that type of thing. Yes, sir.
Because if one side has a weak base and the other side has
Kind of.
like.
Give me a good thought. No.
I
All right, I'm tired of taking questions. We're gonna move on. All right, it's because Cl minus is the conjugate base of a strong acid, so that means the other bases have to be stronger.
That's nice.
Kind of. It was very unclear.
Wait.
I'm not talking about this now.
Okay, can you have 2 strong acids in a reaction?
Two strong acids.
Yeah, like if you have like, or just like two strong acids on the scale, like HCl.
Like together, they would just dissociate, they wouldn't react then.
Yeah, exactly. So then you could say.
Yeah, so no reaction.
If there's one strong acid in the reaction, then you know that the other reactant for the base would have to be, a lot weaker. Or would it couldn't be possible?
No, you can react the strong acid with a strong base.
Oh,
Yes,
could you react the strong acid with a weak?
yes,
Yeah, but like, would that be the lowest reaction?
Yeah.
What if it was a strong base with a weak acid? Okay, okay, so it doesn't, they don't have to be like the same.
yeah. Mhm. That's why we're not comparing these two.
Yeah.
We're comparing the conjugate.
Yeah.
Yes,
You say like H2O, it's a weak base, but like Cl minus. Because HCl is.
yeah, you could. I wouldn't say H2O because H2O is a weird case. I would say that it's amphiprotic instead of weak base. Yeah, you can say it can act as a weak base, but you can't say it is a weak base because it could also be a weak acid. Yeah, that makes sense. But I understand your reasoning, and the reasoning is correct. Yeah, just the terminology, you gotta be a little more specific. Yeah, good question, but
What's the reasoning for the relative strength of the base?
yeah, the reasoning is Cl minus has to be weaker than H2O, because it is the conjugate of a strong acid. And if you look at H2O is the conjugate of a weak acid, H3O plus. Yeah. So yeah, if you want to label this just to make it a bit more clear for you, H3O plus is a weak acid. And so the conjugate is also probably going to be like strong-ish weak, right? Where it's not going to be like super weak like this. Yes, Izzy. Yeah, so technically, so water can be also act as a weak base, and its conjugate is going to be a weak acid. However, this guy has to be weaker because its conjugate is a super strong acid. Yeah, so so since this one is super duper strong, it makes this guy super duper weak. Whereas here, this is weak, so it makes it kind of weak, but it's not like super duper weak.
So if I'm weak, it's like less weak.
Yeah.
Okay.
Yeah.
If the acid is just not strong, but the base will be weaker, the conjugate base will be weaker. And it's just normal acid.
Weaker than what? Weaker than water?
Yeah.
Yeah, usually it's gonna be a bit weaker. Yeah. Yes.
Was that chart with the acids? There's like all of the acids.
There's more. It's just a general, just some of the common ones.
Okay, it's like is there a way to assume like we memorize the strong ones and then we get something else random? We can, like, assume that it's-
Usually you'll be able to predict it based on electronegativity differences. We'll talk more about that later.
Okay.
But as long as you know the strong ones, you should be fine.
So the base on the product side is always weaker than the one. The conjugate base on the product side is always weaker than one on the reaction.
No, because if it's a super weak acid, then the conjugate base is going to be stronger.
Then-
It's basically going to be the opposite.
Okay, but then the reaction will be on to the one.
Yeah.
Or it will go to the right.
Yeah, it's going to lie towards the side that's weak.
Okay.
Yeah.
So
good
the
question.
reaction lies to where the strong will be.
Yes.
Okay.
Mhm. So here it's gonna
Oh, it lies
lie
to
to
where the weak.
lies to the right here.
Yeah.
Good questions, guys. That is so smart. I feel so dumb talking to you guys. It is
Us.
boring. All right. Yeah, I do. Okay, 12.10. Yeah, you got this reaction. I want you guys to take a look at it, and based on what you guys have learned so far, I want you guys to figure out whether equilibrium lies to the left. So I got your term for you here. K is less than 1, or does it lie to the right? K is greater than 1. Okay, so let's take a look at this. So let's identify what these compounds are. So if we take a look at this compound, the first one, is it an acid or a base? It is an acid, correct. Okay, let's go to the next one. Oh, obviously this one's gonna be the base then, right? Okay. All right, let's go to this one. What is the term for SO42 minus? Yeah, not conjugate acid, conjugate base. Yeah, conjugate base, because it needs to turn to the conjugate, so it switches. Which means obviously this one is going to be your conjugate acid. All right, now in order to determine which side equilibrium lies, we basically need to look at the two acids and figure out which one is stronger, okay? That's how we can determine, because the stronger one is going to push the reaction towards the other side. So yeah, which one is stronger? Okay, So let's take a look at our chart. That will help us. So we're gonna take a look at HSO4 and HCO3. So if we take a look here, okay, I got HCO3 right here, and then where's HSO4? HSO4 is right here. So which one is stronger? Yeah, HSO4 is a stronger acid than our than this guy. So let me label it just so we have it. So this guy is stronger. And this conjugate acid is weaker. Okay, so since this compound is a stronger acid, it's gonna push equilibrium towards the right. Yeah, because it wants to dissociate more than this guy wants to dissociate. Okay, so this couple wants to break up more than this couple right here. Okay, so it's gonna push that way. So if equilibrium lies to the right, okay, that means that Kc is going to be less than or greater than 1. Yeah, Kc is going to be greater than 1. And that will be your reasoning. If it lies to the left, that means Kc will be less than 1. So it'll be a decimal. This swings to the right because this compound is a stronger acid. Stronger acids want to break up more. So since it wants to break up more, it wants to go towards the right. All right, let's take a quick 5-minute break and then we'll come back to this. If you have any questions, please double check with me. Okay, so this next section, we are going to be talking about the auto-ionization of water. Okay, so the auto-ionization of water basically tells us, or is basically a way for us to describe how water is weird because it could be an acid or a base. Okay, it's both. Okay, so we got a quick diagram right here. Let me zoom out a little. Okay, so we got a diagram right here. And if you notice, both reactants are water, but the water molecules react with each other to turn into hydroxide, Me, and hydronium. Okay, so that's what the auto-ionization of water is. Basically, water reacts with itself. 2 water molecules react, and then they turn into, it could be an acid or base. Yeah.
How do you tell which one?
You don't. Yeah, it doesn't matter. Yeah.
So
Yeah.
if it's equation like that, either H2O could be an acid or a base.
Yeah, it doesn't matter. We can what is it? Signify one of them to be the acid or the base, but it doesn't really matter. I mean, they don't have like name tags. They're not unique. They're not special. Yeah, Vivian. It collides with each other, and then depending on how they collided, one of them will give the H plus to the other one.
Like that happened in my life.
It's happening right now. It's happening inside your body too.
It is.
Yeah. If you have any container of water, it's already auto-ionizing, going back and forth. It's instantaneous, happens real quick.
I know if I drink it.
What do you mean? You're drinking water, but so water, H2O is okay. So these structures that we draw are actually just averages. Yeah, you're not drinking purely H2O. There's obviously a lot of OH minus, there's H3O plus, there's some H2O, but we don't know the actual like percentage because it's constantly changing, but it averages out to all of them being H2O. Yeah, that makes sense. So remember resonance structures where none of the 3 structures are real. It's the average of the 3. Yeah, it's kind of like that. Yeah. Yeah, one of them, when it's reacting with each other, one of them has to be a base, one of them has to be an acid. Yeah. Yes. Yeah. Now you're gonna look at water. Yeah, it's neutral. It averages out.
But there's still acids.
There are acids and bases in there.
So depending on the temperature, it'll be different amount of.
No, temperature doesn't change that. Yeah, this isn't depending on temperature. That's a great thought, though. No, it's depend. If you have water, just water, it's gonna be like, so water's a standard. It's perfectly neutral. Now different minerals inside the water can change the acidity and basicity. So if you look at like, there's that one brand, it's like alkaline water or something, and it says pH 9.9 or something. I don't know, it's like bougie water that I saw at a gas station. Basically they add minerals to make it a little bit more basic because apparently it'll make it when you drink it, it'll sit better in your stomach than just pure water. But anyway, just water.
Canned water.
Yes.
So that was more.
No, it's just water. It's a scam, guys. The bottled water is freaking tap water. Anyway, Let's move on. Okay, so if we have a equilibrium, if you guys take a look at this, it's a reversible reaction. We are going to be looking at the equilibrium constant. Wow. Wow. Okay, anyway, now if anyway, oh sorry. Warning. All right, anyway. So if you guys notice, the equilibrium constant for water is just the products, because we don't put pure substances, right? So we don't put the waters because they're pure liquids. So we just use the products, hydronium and hydroxide. Hydronium.
That's a cool name.
It is hydronium.
Like, compared to
Water.
water. What would mean water is like official?
Hydrogen dioxide. Oh wait, no, dihydrogen oxide, sorry.
Dihydrogen.
Dihydrogen oxide.
Like, I'm drinking dihydrogen oxide. right
Yeah,
now.
you're also very pretentious.
I went to a show once and they were selling dehydrated.
Oh, yeah.
It was pretty fun.
It's like a, it's like, oh,
Yeah, it's just.
No, it's an empty can. That's funny.
but it's like $20.
Yeah.
It's basically a can of nitrogen then.
So interesting.
78% of it's.
Oh, my fault. 78.
Where did you get?
Is that how many significant figures? Just 2 significant figures? Can't give me more.
I mean, I only know 78.
All right, so one quick thing that you guys do need to know is that so when we have the equilibrium constant for water, there's other ways to express it. Now we can write it as Kw, and Kw is equal to the equilibrium constant of water. So this equation right here. We can also simplify this. So whenever you see H3O plus, you can always just do H plus instead. That's pretty much the same thing. And that's equal to this value at all times at 25 degrees
Why?
Celsius. Because if we simplify this that equation up there, so we got H2O plus H2O, and then OH minus plus H3O plus, right?
Wait, what's the double?
Kw is the what is it? The equilibrium constant for water. Yeah, K water basically. Yeah. We can simplify it as H3O plus as H plus, because if we look at the net ionic equation of what's actually going on, the only thing that's really being transferred is the H plus. That's why.
Is that a constant? Like the. when
This
it's
is a
up there,
constant.
It's always. Like,
This is a constant at 25 degrees Celsius.
Okay.
Yeah. H plus, because the only thing that's happening in this equation is the H plus is moving back and forth. So let me go back to the picture. The picture might be more helpful. So if you take a look at this, right, we can replace this as H plus, because if you separate H plus and H3 from H3O plus, what do you get? You get water, right? H3O plus, you can split this up into H plus and H2O. Okay, you got an H2O on the left side and the right side. These cancel out. So you got H plus, OH minus, H2O. That's why. Does that make sense? Sorry, I should have just gone to the picture right away. That's on me. My fault. Yeah, so it's like the net ionic equation. Okay. Yeah, with that being said, let's move on. So, couple things that you guys need to know is that when H plus concentration is equal to the hydroxide concentration, that's when the system is neutral. So when you have a neutral solution, it is neither acidic or basic, and that's when the concentration of H plus and OH minus are equal to one another, okay? All right, now some things that you guys might want to jot down. An acidic solution is when there is a higher concentration of H plus than hydroxide. And in that situation, it's still going to be equal. The concentration product is still going to be 1 times 10 to the negative 14. Okay. So if you guys notice, the constant between acid, neutral, base is that the concentrate or the product of the concentrations of hydroxide and H plus is always going to be 1 times 10 to the negative 14. Okay. And then, but the thing that changes is that here you have more H plus in an acid. In a base, you have less H plus concentration, and neutral ones, they are equal. Okay, so that's kind of the differences. But when you multiply the concentrations together, you will always end up with the same value, okay? It's like magic, yeah.
The values aren't affected.
Yay!
Hydration.
Yes.
Is that like a reference point?
Mhm. Yeah. It's because the scale is based on water, and so we use water as the standard. Mhm. Mhm. Yes. Alrighty, guys. So with that being said, now that you guys got a bunch of numbers, I want you guys to try 12.11. Okay, this one might be a little bit tricky, but I want you guys to use the information that you guys learned. I want you guys to calculate the concentration of H plus and OH minus in a neutral solution at 25 degrees Celsius. So try that out. 12.11. You gotta think a little bit mathy here. Yep, all done. Okay, not done with the unit for today. Okay, so it says that the values of H plus and OH minus in a neutral solution have to be equal to each other, right? So we're basically going to be using this equation, OH minus, and it's equal to 1 times 10 to the negative 14. Now, if they are equal to one another, we can just represent them with the same variable. So x times x, so we get x squared. Right, and if you just want to find the answer, just find the square root of both sides. X is going to equal 1 times 10 to the negative 7.
Okay, Jess. Thanks so much.
Okay, any questions? Make sense? So again, if H plus and OH minus are equal to each other, we can just use the same variable to represent it. So you can just replace it with x times x, which is x squared. Find the square root. And so in a neutral solution, the concentration of H plus will be 1 times 10 to the negative 7. OH minus will be 1 times 10 to the negative 7. Okay. All right. So let us finish up with one last question. Okay. I want you guys to do 12.12. Okay. So I give you some different concentrations, and based on the concentrations that are given to you, I want you to determine whether the solutions are neutral, acidic, or basic. Some of them you might not have to do math. Some of them you might have to, but that's all good regardless, okay? So let me zoom in. Okay, and I'll give you guys about 2 minutes to do it. Okay, so if we take a look at part A, and you're going to notice that it's 4 times 10 to the negative 9. Okay, now, so if we take a look back at the other picture, okay, we're just gonna take a look at this and see if where H plus will land on these solutions. So it's 4 times 10 to the negative 9. Okay, and so basically what we can do is we can just basically compare it to the neutral solution. So we know that in the neutral solution, both of them are 1 times 10 to the negative 7, right? H plus and OH minus. So if we take a look at 4 times 10 to the negative 9, is this number greater than or less than this number?
Less.
Yeah, it's going to be less than. So if it's less than this value right here, that means it's going to shift. It's going to be, yeah, basic. Not right or left because it's not an equation, but yeah, you get the point. In the picture, it'll shift left. So this will be basic. Okay. If you have a solution where H plus is 4 times 10 to the negative 9, it will be basic. And the reason why is because neutral, right? Neutral is 1 times 10 to the negative 7. So if this number is smaller than 1 times 10 to the negative 7, you have less H plus than at neutral. If you have less H plus, that means you have more OH minus, which means that it's going to be basic. That makes sense? Okay. Woohoo! All right, let's go to the next one. Next one should be easy. This one is, yeah, neutral, because both of them, H plus and OH minus concentrations are 1 times 10 to the negative 7 at neutral. All right, now this one right here might seem a little bit trickier because it's in concentration of OH minus, not H plus, but we can use the same reasoning. Now, if we take a look at this and compare it to the neutral number, is this number smaller or greater than this number right here? Yeah, it's smaller. Okay, so since it's smaller and we're talking about OH minus, do we have more OH minus or less than at neutral? Yeah, we have less OH minus than at neutral. Okay, so if we have less OH minus, is it acidic or basic? Acidic, exactly. So that's one, those are some ways you could think about it, okay? Now, if you wanted to be a scholar, you can do the math and calculate all that stuff, but I mean, you can just use your reasoning like this, okay? All right. All right, so we're gonna do one.
I love those little strips.
I did
We do have those strips.
On school water, my birthday time.
Yeah, can we just keep it in school water?
Sure.
It's
It'll
not
come
gonna
out
be
neutral.
filled with
Actually, it might be a little bit basic. Alrighty, guys. If you guys can, please log off your Chromebooks. You guys can put the chairs up.